Solar photovoltaic system, the system which converts sunlight into electricity. That is nothing but the photovoltaic system. So here it is called as solar photovoltaic system. The solar generates the sunlight that converts into electricity. That's why it is called as solar photovoltaic system. So it mainly contains the so the main advantage of using solar photovoltaic systems are it is reliable, it is durable, and generally maintenance is free. So less distribution network is required. The major disadvantages are cost, low efficiency, large area required to generate desirable power output. Solar energy is intermittent, hence backup power supply required. Why? Because solar energy is only available during daytime. So during nighttime there is no availability of sun. So that we have to no generation of solar energy in the nighttime. So we have to use the backup or batteries for storage of power during night times. So mainly we are using the semiconductors. So a semiconductor material is one whose electrical properties lies in between those of insulators and conductors. The examples for semiconductors are germanium and silicon. So in terms of energy bands, so semiconductor can be defined as the materials whose the energy gap between the conduction band and valence band with a narrow of gap of 1 electron volt. So we know that we have two types of semiconductors, intrinsic and extrinsic semiconductor. So intrinsic is nothing but a pure semiconductor is nothing but a intrinsic semiconductor. Extrinsic semiconductor or it is a impure semiconductor. The examples for impure semiconductors are N-type and P-type semiconductors. So, intrinsic semiconductor, a pure semiconductor whose Fermi level is or energy gap in between the valence band and conduction band. So, when the light energy is falling on the valence band, where the electrons will move from valence band to the conduction band so that it electrons will be excited so that the conduction band is partially filled and valence band is also partially filled. So a pure semiconductor is called as intrinsic semiconductor. Second one is extrinsic semiconductor or it may be called as impure semiconductor. Impure means mixing. So those intrinsic semiconductors to which some suitable impurity or doping has been added in extremely small amount, then they are termed as extrinsic or impurity semiconductors. So basically the extrinsic semiconductors are classified into two types, N-type semiconductors and P-type semiconductors. So where in N-type semiconductors the majority are electrons and the minors are photons. Whereas p-type semiconductors, the majority are holes and the minors are electrons. So n-type semiconductor. So this type of semiconductor is obtained when a pentavalent material like antimony is added to pure silicon crystal. So in n-type semiconductors, electrons are the majority carriers while holes are the minority carriers. So coming to the p-type semiconductor, this type of semiconductor is obtained by tracing of trivalent like boron or added to a pure silicon crystal. In this case, the three valence electrons of boron atom form covalent bonds with four surrounding germanium atoms, but one bond is left incomplete and gives to a hole, as shown in the figure. So, is acceptor impurity creates a hole. So in this type of semiconductors, the holes are majority carriers, whereas electrons are the minority carriers. So this is the diagram of solar photovoltaic system, where when the sunlight is falling on the semiconductor, so that the electrons will flow, so that it produces the electricity and supply to the load. So we have the p-type semiconductor and n-type semiconductor, which is separated by some junction, p-n junction diode. So when the light energy is falling on the junction, so that the holes in the p-type silicon will move to the electrons, and electrons in the n-type semiconductors will move towards the hole, so that the junction will break, so that the flow of current takes place from holes to the sorry, from p-type to the n-type semiconductor. So it creates electric current, so that that electricity will be supplied to the load. So PN junction is a boundary or interface between two types of semiconductors. One is p-type semiconductor and n-type semiconductor, separated by the junction. So PN junctions are elementary building blocks of most semiconductor electronic devices such as diodes, transistors, solar cells, LEDs, and integrated circuits. So depletion region in PN junction. You know that when P and N-type semiconductors are combined, it forms a junction generally termed as depletion region. So when a voltage of zero point 0.3 volts or zero point 0.7 volts is applied, so that the junction will break, sufficient voltage is applied, that is called as cut-in voltage. When a cut-in voltage of more than zero point 0.7 volt is applied to the PN junction diode, then the holes in p-type semiconductors will move towards the n-type, and electrons in n-type semiconductors will move towards the p-type, so that flow of electricity takes place. So energy available in a photon. So we know that E is equal to hc by lambda, which is nearly 1.24 by lambda into electron volt, where h is a Planck's constant. So for silicon, the maximum efficiency is 32.9%, means conversion of that solar energy to a maximum of electricity is 32.9%. So this is about the energy band gaps, where the band gap is the distance or gap between the valence band and conduction band. So for silicon, it is less than 1.1 electron volt, whereas for gallium, it is 1.4 electron volts. For aluminum, it is less than 1.7 electron volts. That is the energy gap between the valence band and conduction band. So types of band gaps, that is direct band gap and indirect band gap. Okay. So direct band gap means the top of the valence band and the bottom of the conduction band occur at the same value of moment. Whereas indirect band gap means the maximum energy of the valence band occurs at different value of momentum to the minimum in the conduction band of energy. That is, the example is silicon. So these are the current voltage characteristics of solar system. So this is a power, where power is a product of voltage and current. So maximum power is nothing but it is a product of voltage and current. P max is nothing but V max into I max. So this is a curve that drawn between the current versus voltage and power versus voltage, where on x-axis we have the voltage, on y-axis we have the power and current. So the power delivered by a solar cell is the product of current and voltage. With the solar cell open circuited, that is not connected to any load, the current will be at its minimum zero and the voltage across the cell is maximum. So here, when the current is zero, V is maximum. When V is zero, current is maximum. Why? Because when the solar cell is short circuited, the positive and negative leads connected together so that the voltage across the cell at its minimum zero, which is known as solar cell's short circuit current. Next, this is the IV characteristics so that the solar cells are connected in series, parallel, and single. The solar cells are connected in series, the solar cells are connected in parallel, and a single solar cell. These are the characteristics that is drawn between voltage versus current and voltage versus power. So, short circuit current, open circuit voltage, and maximum power, that is PVs. So, IV characteristics of solar cell. So, if we take the fill factor, generally it is the quality of measurement of a solar cell. So it is calculated by comparing the maximum power to the theoretical that would be output at both the open circuit voltage and short circuit current together. So form factor is P max by PT, that is P theoretical. Theoretical maximum power and the maximum power that occurs when we have the current and voltage both are at maximum value. That is IMP, that is maximum power, current value, maximum point voltage value by ISC into VOS. So efficiency is calculated as the ratio of electric power compared to the solar power input into the PV. So this is the IV characteristics of solar cell that is based on the temperature change. When the voltage decreases, the value of the current and voltage, how it varies and can be shown in the figure. So here, when there is a decrease in 0.5 degree percent for 1 degree in voltage, there is an increase of current of plus 0.05% of current per 1 degree centigrade. Means, so when PV cell is exposed to high temperatures, ISC increases slightly while VOC decreases more significantly. Why? Because here current is 0.05% increase, whereas voltage decrease by 0.5%. Means because of temperature rise, the open circuit voltages decrease will be more significant as compared to current. So this is a PV system. This is a solar cell, solar module, solar panel, and solar array. So a single cell is solar cell, where the solar cell is connected in rows and column, that is solar module. If it is arranged in both in different horizontal and vertical ways, that is comes under the solar array, that is nothing but the solar panel. So this is the module structure of solar PV module. So typically the solar cells are connected 36 connected in series so that you can calculate the what is the maximum current, maximum voltage that occurs in the solar PV array. So this is the typical diagram of 36 solar cells connected in series. Here, 1, 2, 3, 4, 9 that are connected in 9 fours are 36. Totally, so 4 solar panels where 36 cells are connected in series. You know that the output voltage is always DC voltage for solar. So this is a maximize the solar PV output and load matching. So mechanical tracking and orienting the panel to receive maximum solar radiation. Electrically tracking the operating point by manipulating the load to maximize the power. So this is a maximum power point tracker so that when the maximum power will occurs by tracking the solar PV panel. So maximum power point tracker is a DC-DC switching voltage regulator. They take the DC input from the solar panels, change it to high frequency AC, and convert it back to a different DC voltage and current to exactly match the panels to the batteries. So maximum power point tracking is electronic tracking, usually digital, where the output voltage is the product of input voltage with respect to the duty cycle of the MOSFET, where D is the duty cycle. Duty cycle is nothing but it is a ratio of T on, that is on time by total time, that is on time plus off time of the switch, that gives the output voltage of the solar PV panel. So output voltage depends on duty cycle of the electronic device like MOSFET, IGBT, whatever the electronic devices that we are using. That is about the maximum power point tracker.